So, now we will discuss semiconductor physics or physics of semiconductors or semiconductor crystal. Okay. So, this we know the band structures. So, in a crystal there are many bands, right. Now, I have explained you that if we have so take just two band, other is filled. So, take upper this filled one or partially filled and this empty band. Okay. So, I think this has gone out. So, this is one band. Okay. So, as I mentioned you that if this band is filled, completely filled, and this band is empty, okay, and this difference between these two is called band gap Eg, right. So, depending on this Eg, then we decide whether it is semiconductor or insulator, right. So, if Eg is in the range of generally is say generally less than 3 electron volt, more or less, it is not exact. If it is less than 3 electron volt, okay, then it is behave like semiconductor at room temperature or above room temperature. But at t equal to 0, all the time, as I told that there is no carrier, okay, to conduct. So, it behave like insulator, right. When Eg is quite high, as I told, is generally greater than 3 or 4 electron volt, whatever. So, then it will behave as a insulator, right. And when Eg equal to 0, that means these two overlap, there is no gap between these two, then it will have this electron will have many energy levels to move. So, we will get conduction electron and then it will behave like metal. So, that I have discussed with you. Okay. So, in semiconductor, basically this band structure, whatever we got this band from band theory of solids, whatever we got this concept of band. So, that will be useful to explain this physics of semiconductor, means whatever the semiconductor shows different property, electrical property mainly. Okay. So, that will be explained based on this band structure. Okay. So, this is one way to distinguish or differentiate among the semiconductor and other insulator, but in terms of carrier concentration in a crystal, that also one can use for differentiating the this material, electrical property of the material. So, carrier concentration, generally what is the range of carrier concentration? Carrier carrier concentration. What is this? Number of carriers, it may be electron. In case of semiconductor, it can be hole also, okay, or this combination of these two. So, that is the in general we tell carrier. So, carrier can be electron or it can be hole also. So, carrier concentration. So, this now you just consider the electron concentration in the material. So, this generally this range for it is semiconductor, its range is its resistivity, its range is I think this is 10 to the power around 13 say to 10 to the power yeah, around say 10 or 70. It is not exact, but this is the range. Okay. In this range, this and then this is the semiconductor. In this range, this semiconductor. In this range, this semi metal, and in this case, it's the metal. Say. So, this metal generally it's 10 to the power 23, 10 to the power 22 to 23 I guess, 10 to the power 22 to 23, yes. This is concentration, this is the concentration of electron. So, this per unit cc means cubic centimeter. So, this number of electrons per unit cube centimeter. So, that is the typical number. So, this is the semi metal. This is metal, this is semiconductor. So, its concentration, if I put some concentration of electrons or carriers in some material, so I can if I put a just line like this, if I just put a line like this, so say this is the concentration of germanium, and this is the highest concentration here is basically it's around it is copper. So, in copper this number of electrocarriers is very high, it is around 10 to the power 23, and in germanium it is around 10 to the power 13, it is almost half of that copper. Okay. And in semi metal basically here this copper and then I think sodium like this concentration, and then I think this is another metal, this is potassium. Okay. These are concentration, and this semi metal it is arsenic, antimony, graphite, bismuth, arsenic, it's antimony, graphite, bismuth. Okay, these are look semi metal. So, semiconductor and metal, so their concentration is in between. So, it is semi metal. Okay. So, this what I told, this the graphite, this is the bismuth, and this is the arsenic, antimony, arsenic, and there is the other one is antimony. This is the antimony and this is the arsenic. Okay. So, this behaves like so this knowing the concentration of the material also one can tell about its electrical property, because there is concentration this EDM bar electrical conductivity it depends on this concentration. What is the electroconductivity? That is N, this concentration of carrier, NeV, NeV, drift velocity, divided by, because that NeV, that is the basically current density. Current density equal to sigma E, right? Current density sigma E. So, if you divide by this E, so then that is a, so V by E generally, what is this? V by E Ne, that is the mobility, drift velocity per unit electric field, that is mobility. So, this concentration depends on the carrier, this conductivity, it depends on the concentration of carrier and the mobility of that carrier. So, thus this from concentration of the different material, one also distinguish the that metal, semiconductor, semi metal, and this insulator basically in this side, if you go to the lower side. So, this side it will be insulator. So, forget, we are not interested about insulator now. So, and also it the semiconductor, when you increase the temperature, so it shift towards this. Okay. If shift towards this, so its concentration will increase. Okay. Its concentration of carrier will be higher at higher temperature. So, this way one can. So, important fact is that concentration of electron or carrier in a material and the band gap of the material, these two are very important for say in this case for the semiconductor. Okay. So, concentration of carrier and this band gap. Okay. And for semiconductor, it is clear that all the time this lower band is filled, okay, upper band is empty. So, this band is called valence band. So, now I am going towards the, just we will concentrate now for this semiconductor. Okay. So, these are basically, these are valence band, these are valence band, and these are conduction band, right. So, Eg is here their band gap. Now, so this energy generally we consider this. So, top edge, band edge of valence band, this energy is Ev, and bottom edge of the that conduction band, that this energy we consider as a Ec, right. Now electrons are distributed in this band, right. Electrons are distributed in this band. So, at t equal to 0, all electrons are here distributed here, right. Now, when t is higher, then what will happen? So, some electrons will be excited from valence band and will go to the conduction band, right. Then there will be vacancy here and it will be partially filled one, right. So, this absence of this, so from here this whatever electrons are there, so that will go, electron will go here, okay, due to applying thermal energy, due to increase the temperature of this semiconductor. Okay. Then some electrons from top band, from the upper edge of this valence band will go to the lower edge of the conduction band, right. So now, so this absence of electron here, this will behave as a hole and this will behave as a conduction electron. So, two types of carrier will be present in semiconductor, one is hole and another one is electron. Okay. Now, what happened, this electron from here, electron is going there, fine, but sometimes this electron also come back and recombine with the hole, right. So, this is called recombination process, recombination process. So, then we will lose a pair of electron, pair of hole electron. Also, when one electron goes from here to there, so then we generate a pair of hole electron, right. So, the generation of hole and electron, pair of hole and electron, and recombination of pair of hole and electron, that all the time it goes on, right. In the system it goes on, and at a particular temperature, it comes at a equilibrium condition, right. So, when it will come in equilibrium condition, when rate of generation and rate of combination, these two will be equal, right. So, rate of generation and have to be equal to the rate of combination at a particular temperature when the system is in equilibrium condition. Okay. And this generally this is proportional to this generation and recombination, it is basically proportional to the concentration of the carrier, it is proportional to the concentration of the carrier. See, if I take proportionality constant C and then this concentration of electron and concentration of hole, if I take N and P, this N is hole electron concentration and P is hole concentration. Okay. So, this now, if in principle this number of this this hole concentration must be equal to the electron concentration, because all the time they are either they are generating in a pair or recombining with in a pair. Okay. We are losing a pair or we are generating a pair. So, this N must be equal to P, N must be equal to P, and then this G equal to R equal to C N square, right, N square. So, now this case we are writing Ni Pi, okay, Pi, just to define this type of semiconductor is called intrinsic semiconductor. It is called intrinsic semiconductor. Intrinsic semiconductor. Okay, or pure semiconductor, pure or intrinsic semiconductor. Okay. So, this ohm meter, so this okay. So, this you know this there are some, so these are basically intrinsic semiconductor, and there are very familiar semiconductors are there. So, you know these group 4 atoms generally group 4 in periodic table group 4 atoms. So, when they form crystals, so they are basically semiconductor. So, like in group 4 what are the carbon are there, then silicon, then germanium, then you have tin and then palladium, then tin, Sn, then palladium. Okay. So, this carbon when they form crystal, this carbon band gap is generally here band gap Eg for this material it is around I think 5.51 electron volt, 5.51 electron volt. Okay. For silicon it is 1.16 electron volt, for germanium 0.72, 0.75 electron volt, and this tin it is very small 0.08 kind of 0.08 electron volt, and this nearly it is 0. Okay. So, this electron volt whatever mentioned that I have mentioned at T equal to 0, at absolute temperature T equal to 0. Okay. So, at room temperature, this although it is in group 4, but this band gap is so high. So, it is insulator even at room temperature it is insulator, and at room temperature these two shows it is the metal behavior okay, because band gap is almost negligible. So, it is metal, and these two behave like semiconductor, because that is why I gave you this band gap range is very important. It's if it is less than 2 or less than 3 electron volt. Okay. So, then only it will be because so that range. So, whatever energy will give, kinetic energy will give kT, what is the temperature it will reach. Okay. So, that temperature that energy, kinetic energy that should overcome this band gap Eg, right. Okay. So, kT has to be is comparable to the Eg. So, if it is very high, so you need very high temperature, and in principle you cannot apply that high temperature and it will not be useful. Okay. So, these are intrinsic semiconductors, and there this concentration of hole and concentration of electron are equal. Okay. Now, so here this it is just because of thermal energy changing the temperature, you can change the concentration of carrier. But another way is there to manipulate the concentration of carrier in the semiconductor. So, that semiconductor that is called the impurity or what is this appropriate one, impurity or intrinsic semiconductor. Different names people tell in different way, different name. So, this impurity or extrinsic semiconductor, in this case so as if this carrier constant, controlling the carrier constant is very important in semiconductor. Okay. So, I have a semiconductor, say silicon semiconductor, it has band gap 1.16 electron volt. Okay. And so, it as intrinsic, it's depending on temperature I will get some carrier concentration. So, nothing else I can do, but there is a process, it is called then it will be called that impurity or extrinsic semiconductor, when those intrinsic semiconductor are doped with some dopant, with some atoms, either which will give electrons to this semiconductor or it will give hole to the semiconductor. Okay. So, if you dope with some impurity or some atom, so that your intrinsic crystal, intrinsic semiconductor crystal, so it will have additional electrons or holes, right. When it will get additional electrons, then we will get it is p type semiconductor, or when it will gain that after doping, when it will gain this gain electron, then it will be called n type semiconductor. Right. So, this either p type or n type. So, this is because of doping in the system, and we will get this more hole in this semiconductor or more electron in the semiconductor. So, that we can control when concentration of carrier will change in the system, we can control the electrical property of this semiconductor, right. So, this I think you in case of the say take silicon have 14 electron, right. So, it is distributed 1s2, 2s2, 2p6, right, 3s2, 3p2, right. So, these are filled. So, these 4 are valence electron, these 4 are valence electron. Okay. So, as per octet rule, outside orbital always or shell always it try to have the 8 electron. Okay. So, each silicon atom will have 4 valence electron. So, it will try to share so there is silicon, that silicon atom, okay, silicon atom, it will form a lattice. So, how it is formed lattice? So, these are basically it is core of silicon having 4 positive charge, right, and then it will form bond. It will form bond with other 4 silicon, neighbor silicon. Okay. So, here also similarly we put this basically positive 4 charge. Okay. So, then it will again, so this way they will share electron. Okay. Okay. So, this way will form covalent bond. Okay. So, they are sharing. So, this it has 4 electron and it is shared with other 4 electron, right. Okay. So, now when you basically increase for intrinsic case, in intrinsic semiconductor, when you increase this temperature, it is at particular temperature, then basically if this one of the electron, it may leave this side, okay, leave this side. So, it come here, then this the absence of electron, it is treated as a hole, right. So, a pair of hole is generated. Okay. So, that is basically coming from this bond, okay, breaking this bond, it is going, and then absence of that one. So, it will fail to have one electron to again make this bond, okay, to repair this broken bond. So, that is why some other electron can jump here. So, this electron can jump here. Okay. Now, it will be hole generated here. So, as if this now hole is moving this side. So, from here it is moving this side, okay, and electron are moving this side, okay, electron are moving this side. So, hole and electron, they are moving. So, they are this conducting in the system. Okay. So, anyway, so what I want to mean here. So, now if you doped with this silicon with some group 3 element. Group 3 element, what is the group 3 element? I think aluminum is group 3 element, and then boron, gallium, indium, right, boron, gallium, indium. So, aluminum, boron, gallium, indium. So, these are group 3 elements. So, one of them if we pick up and doped with this. So, doping is very small. I generally tell this ratio is 1:10 to the power 6 or 7 also. Okay. So, here this out of 10 to the power 6 atom of silicon, one will be replaced by this impurity, one will be replaced by this say group 3 element. Okay. So, now, so it has 3, group 3 means it has valence electron 3, it has valence electron 3. Okay. So, then this valence electron 3, so its positive charge is 3, core 1, this core 1 is positive charge 3, and then so it will share this 3, it will share with the others, this 3 is 3 electron, but 1. So, this silicon will miss another electron. So, this bond is not complete. So, all the time this silicon will try to have the one electron to complete this bond, but there is absence of this electron here. So, it will be act like a hole. So, there is absence of electron here. So, it is as if it is a hole, it is giving a hole to the system. So, it is the system now can accept electron, right, the system can accept electron. Okay. Yes. So, these the in this ratio as I told 1:10 to the power 6. So, in that ratio if you doped say some amount of this one of them group 3 element. So, you will get hole in the system, you are generating hole in the system, depending concentration will depend on this. So, here now in this case you have intrinsic carrier, all the time it will be there, okay, and they are equal. Now, here additionally you are getting this hole in this system. So, hole concentration. So, this concentration is generally higher than the intrinsic concentration. Okay. So, this whole concentration here, it will be higher in this system. So, it is that is why this in this system this carrier, majority carrier is hole, this hole is called majority carrier, and in whatever the electrons are there. So, these are called minority carrier. Okay. So, this type of semiconductor is called p type semiconductor. If you doped with this that is 5 group of element, what is that? The phosphorus, and then antimony, phosphorus, antimony, and then people use generally let me some others I have I think yes, phosphorus, antimony, arsenic, yes, because these are very, whatever I am reading, these are practical one. So, generally these are used frequently for this for getting this p type or n type semiconductor. So, these are pentavalent, right. Earlier was the tetravalent, these are pentavalent. So, 5 valence electrons are there. Okay. So, when it will put 5 electrons are there. So, its positive charge, core 1, these 5 charge, positive charge will be there, and it will leave 5 electron. So, 4 electron will be taken by this neighbor, this 4 this silicon, and 1 electron will be extra, nobody is there to take it to form the bond. So, then the system will have this additional electron from the doping. Okay. So, now in this case this electron concentration will be higher, and this whole concentration will be lower. So, for n type, so this n electron will be majority carrier, and this whole will be minority carrier. Okay. This whole will be minority carrier. So, now in this band here, this dopant whatever we are putting, either this tetravalent or pentavalent. So, there they have energy level from where they are giving the electron, valence electron they are giving. So, that energy level of that one, the donor, okay, it is just generally is below the conduction band, but close to the conduction band. Okay. And this in case of silicon, this difference is these are very close, it is in the range of 0.02 electron volt. Okay. Okay. So, these are called, this is called donor level. This is for n type, this is for n type semiconductor. This level can donate electron, is donating electron to the silicon, to the conduction band of the silicon. So, that is a donor, and it is very close to that also, it is donating. So, it is giving electron, conduction electron to the system. And in case of this p type semiconductor, so tetravalent, so it accepts a level. So, this from this there is a level, there is a shortage of electron, right, shortage of electron, 3 electrons are there, because for bonding we need 4 electron to satisfy the all silicon. So, one bond is not satisfied. So, as if, so this is called acceptor level, it is called acceptor level. Okay. Acceptor level. So, that energy level from where these electrons are, valence electrons are coming from tetravalent atom impurity. So, this it is close to this, it is at the top of the valence band, and also it is very close to the. So, this also energy is difference is in this range. Okay. So, this this is the more or less this band structure of this band structure schema, the structure of this that p type and n type semiconductor, and this so we are doping the semiconductor, intrinsic semiconductor, because of temperature, its concentration changes, carrier concentration, and in case of doping, because of doping, type of doping, the concentration of carrier changes, either hole concentration or electron concentration. So, concentration is very important. In next class, basically we will try to calculate concentration of carriers in intrinsic semiconductor, p type semiconductor and n type semiconductor using the this Fermi distribution. So, thank you for your attention. I will stop here.